Let's see. Okay. Hello, everyone. My name is Yiming Zhang. I'm a PhD student of Dr. Heilemann and the University of Arizona. And the topic of this presentation is called Learning Outcome Graph Optimization. In this presentation, I will talk about the basic idea, some concepts related to learning outcome graph optimization, and why we do that. And by the end of the presentation, I will show some simulation results, and we can discuss our future steps. So this is an outline of this presentation. Firstly, I will go over curriculum complexity, including its definition, how we calculate it, and its relation with students' performance. Then I will talk about the course graph and the learning outcome graph, including their relations and the differences. And after that, I will talk about learning outcome graph optimization, and including the objective functions, the constraints. And after that, I will show some simulation result and comparisons. And by the end of the presentation, we can discuss our next steps. Okay, so firstly, this figure is a simulation result of students' completion rate in terms of structure complexity. So the horizontal axis means structural complexity of a curriculum, and the vertical axis means students' completion rate. And these dots are simulation results. We can tell from the regression line here, the students' completion rate drops down as structural complexities increases. So if we want to, which means if we want to increase students' performance, we better decrease the curriculum complexity as much as we can. And in the next couple of slides, I will go over the definition of curriculum complexity, how we calculate it. Okay, so these graphs are a small portion of a curriculum. In this graph, each node means a course, and each edge means a prerequisite. A prerequisite is a prior knowledge you need to know before you study a new course, and the number in each node means a complexity of a course. Based on our definition, the complexity of a course contains two parts. They are delay factors and blocking factor. Delay factor means the length of the longest chains that goes through the nodes. For example, for this node E102, the length of the longest chain is 4, and that's why the delay factor for this node is 4. And similarly, the length of the longest chain through this node is 3, and that's why the delay factor is 3 here. For the blocking factor, it means the number of nodes that get blocked from by a particular node. For example, for this node E105, there's only one node get blocked by this node here. That's why we have a 1 here. And by the end of the chain, there's no nodes get blocked from. So that's why we put zeros here. After we figure out the delay factor and the blocking factor for all the nodes, we sum them together. Then we can get the complexity of all the nodes, like it's showed here. And after we figure out the complexity for all the nodes, we sum them together to get the complexity for the curriculum. And by using our curriculum analytics toolbox, the whole process can be done automatically. And in the next slide, I will show an example. So as you can see here, this is a screenshot of our toolbox. So after you enter the information of all the nodes and the prerequisites, the curricular complexity can be done automatically, and you can check the information of all the nodes as you wish here. So far we have talked about the curriculum complexity, prerequisites, stuff like that, and in the next couple of slides, I will talk about the new concept, which is learning outcome. This is an example from our EC website. As you can see, there are a list of information shows here, including the course number, the name of the course, a brief course description, and the final parts, which are learning outcomes. So what is a learning outcome? I think the definition is after you learn a course, you can obtain a set of skills or points of knowledge from that course. I think that's a more detailed description about a course. And based on information of learning outcomes, a student can tell whether this course is interest him, or if it's necessary based on his plans. So after we gather the information of learning outcomes like this for all the courses in a curriculum, we can put them together and create a learning outcome graph, which should look something like this. So in this graph, each node means a learning outcome, and similarly, each edge means a prerequisite between pairs of learning outcomes. So far, I have talked about the learning outcome graph and the course graph. So it would be very natural to think about putting them together like this. So I think the ideal is we can find a way to map the learning outcome graph to the course graph. So it's like a learning outcome graph is an underlying structure of a course graph. So in the course graph, each prerequisite we have, for example, here, each prerequisite we have between a pair of courses. It means we always have one prerequisite or multiple prerequisites between groups of learning outcomes. Remember previously I go over the curriculum complexity definition, and we find that the curriculum complexity is closely related to the number of prerequisites in a course graph. And the ideal is if we want to reduce the complexity, we better reduce the number of prerequisites in the course graph as much as we can. And if we want to achieve that goal, one way to go is that we can find the proper way to group the learning outcome together, so that the number of prerequisites between each pair of groups can be minimized. So our question at this moment is how we can find that proper way, and the answer is by applying learning outcome graph optimization. And in the next couple of slides, I will show you the process of learning outcome graph optimization.
Can you go back?
Yes.
So if you look at the learning outcome graph,
yes,
look at the first column. It says L1, 1 underneath it, and then the next after it, it says L1, 2. What does 1 and 2 mean in this setting? What does that mean?
Actually, these are indexes. So
it's an index. Okay.
Yeah,
so
index.
This is the same learning outcome, but it's used twice, or it's index. Yeah. What is that? Yeah. What does it mean?
So for example, for the first 4 learning outcome, you can tell from their index. The first one is called L11, the second L12, L13. So it means I group these 4 learning outcomes to the first course.
Oh, I see. So these are okay. So it's L sub 11, L underscore 11, right? L index 11. Not okay. Got it. Okay.
Yeah.
Okay. So just the formatting. It's a formatting. Okay.
Yeah. And this is another example of learning outcome graph and the course graph. So in this case, each green node means a learning outcome. So we have, in this graph, we have 8 learning outcomes in total. And each gray node means a course, and we have 3 courses in total. By doing the learning outcome graph optimization, we use 3 matrices, which are listed in the right side. They are learning outcome adjacency matrix, learning outcome hour matrix, and the learning outcome assignment matrix. I will explain them one by one. So the first matrix is the adjacency matrix for the learning outcome graph. So for this, yes. You have a question? No, no question. Okay. So for this matrix, we have all the blank units are zeros. So we have only zeros and ones in this matrix. And each one we have here means a connection between a pair of learning outcome. For example, for this one, it means we have a connection between the first learning outcome and the second learning outcome, like here, and so on and so forth for the rest units. And the second matrix is hour matrix, which means literally number of hours we need to spend to learn each learning outcome. So number two here means we need to spend 2 hours for the first learning outcome. And number 3 means we need to spend 3 hours. And the last matrix is called assignment matrix, which means how we are going to group the learning outcome together into courses. So the rows here means the learning outcomes, and the columns here means the courses. And for example, in the corner of this matrix, we have a 1 here. It means we assign the first learning outcome to the first course, and the second one here means we assign the second learning outcome to the first course, like here, you see. And in the optimization, we treat the first 2 matrix as input and the third matrix as output. And here they are listed here. And the right side are the sizes of the matrices. S means the number of learning outcome, and the T means number of courses. And the objective function of is listed here. So it's a nonlinear optimization, and the denominator is quadratic. So what the denominator calculates is the number of prerequisite between the number of prerequisites between each pair of courses. And after we calculate this part, we divide it by itself plus a small number epsilon here. So by the end of the calculation, this fraction would always equal 0 or 1. 0 means no prerequisite. 1 means we have a prerequisite between a pair of courses. And then we do a summation for all the pair of courses and get the total number of prerequisites. And we want to minimize the whole thing. The constraints, we have 3 types of constraints here. The first constraint is about how we assign the learning outcome to courses. The goal for the first constraint is that we want to assign each learning outcome to 1 course and 1 course only. We don't want repeated assignment. And for the second constraint, we want to limit the range of hours for each course. We can set the minimum hours here and the maximum hours here as you specified. And finally, for the last constraint, we want to avoid cycles in a course graph, which means, for example, it would be infeasible if course A is a prerequisite of course B, while course B is a prerequisite of course A. We certainly don't want that to happen. That's why we put a constraint like this. And in the next couple slides, I will show you some simulation results. The optimization solver we use is Garobi. So these two are screenshots from the output of an example from Garobi. So you can see from the left screenshot, we can see the basic information of the problem, and we can keep track the process when Garobi is running. So the way Garobi searches for solutions is like iterating through a search tree. So it keeps expanding nodes, and you can see the number of nodes explored and the number of nodes unexplored, and you can see the incumbent objective values like this. Also, if you are trying to solve a rather complex problems, you can set the time limit and the number of solutions you want to save after each run of a simulation. So for this case, I set the number of solutions I want to equals 11. So you can see all the solutions are optimal, and these are the output of different solutions. You can save them for further analysis. And in the next slides, I run our optimization algorithm on the sample degree plan of our ECE curriculum at U of A. So you can see all the courses and the prerequisites are shown here from our toolbox. And based on the information I entered in the toolbox, we can calculate the complexity here. And you can see all the information of nodes if you want. And after we run the optimization algorithm on this example, this is a new sample degree plan we get here. We can see both the number of prerequisites and the curriculum complexities drops down compared to the original degree plan. And I think at this point, one thing I want to point out is that since the optimization is about global optimization, I really don't restrict the range of movement for learning outcome. That's why for some pair of courses, the algorithm could totally put some learning outcomes for example, belong to an English course with some learning outcomes belong to a math course together. So I think in the future, I need to either add more constraint to limit the range of learning outcomes, or otherwise we can rename some courses based on our specification. So I think, yeah, that's it for the presentation. And I think these are our future plan for the next steps. So firstly, we are targeting to get more practical data sets on different programs to the algorithm. And for more complex example, we will design a balanced graph partition algorithm to speed up the process. And like I described previously, we can also apply different dimensional information to the optimization. Yeah, I think that's pretty much of it for my presentation today. Any questions?
Can you go back to the optimized curriculum to the previous slide? So, well, okay, let's start with this one. Okay.
Okay.
So in here, for example, is this the real program, the ECE program at University of Arizona?
Yeah.
Okay. So let's take one of those. Let's see. So the first semester calculus here, in term 1, it's a prereq to calculus 2, to introductory mechanics, and to discrete mathematics. Now let's go to the next one. So here, it's only prerequisite to something in term 7. Why is that?
Yeah, that's what I described previously. Since I did not limit the range of the learning outcome movement, so it could totally be possible that we group some learning outcomes which has not much relation into one course. That's why this could happen. And the overall idea is to reduce the number of prerequisites, since I think even though at this point some prerequisites look very
yeah, you're right.
Yeah.
You're right, but the constraint, I mean, obviously calculus 1, first calculus should be prereq for calculus 2. And it's not in this one. It has no bearing on calculus 2. So is the learning outcome from calculus 1 not relevant to calculus 2?
I didn't, it's not about relevance. I didn't consider the similarities between learning outcomes in the optimization, So in the optimization, each learning outcome in the learning outcome graphs are treated equally. Not not based on our understanding. For example, the learning outcome in English should be very different from learning outcome in math. You know, they are treated equally. So that's why you can see something like this. Yeah, I think that's what I'm going to do in my next steps to make it looks more reasonable at least. But the overall idea is to try to reduce the number of prerequisites as much as possible. Any other questions?
Okay, I have great job, Yiming. One question. So the original curriculum, you optimize the learning outcome and has a new. Yeah. So for this, for example, let's take the same example, which is first semester calculus. Now, in the optimized curriculum, you have different learning outcome for first semester calculus. Am I right?
Yes.
So, but you didn't rename the course. You just take the same name of the course, and so okay. So that's my. I think this is something as well you need to think about after you cluster or partition some of the learning outcomes in a course. You create a new course, like it's not the same course anymore.
Yes, I didn't change the name for the optimized plan. So I think in the future it should be reasonable to change the names if, you know, for some courses which has a combination of different type of learning outcomes instead of one type, you know.
Okay, I understand. Yeah, this is my question.
Okay. Any other questions?
So can we see again the next step slide?
The next slide?
Next slide.
Okay.
Yeah, this one.
Yeah.
Okay, design balanced graph. So what do you mean a balanced graph partition algorithm?
Say it again, sorry.
So what do you mean about design a balanced graph partition algorithm?
So like I said previously, in the constraint, we need to limit the range of learning outcomes or the number of hours for each courses. So in general, for most courses, the hours are pretty much the same, and that's why we want to use this information. That's why we need to design a balanced graph partition algorithm instead of a general graph partition algorithm, which could help to speed up the optimization process. No.
Okay.
Any other questions?
I think I'm good. Any other questions, guys?
That's it?
That's it.
Okay. Thank you. Thank you very much.
Yeah, thank you. I'll stop the recording right now.